Hello everyone. In the last topics, I explained how to form a protostars from a molecular cloud. In these topics, I'd like to explain the protostars. And I would like to find out the path of a protostar to follow on the HR diagrams using the simple model of a protostars. So as I explained, we only consider a very simple model of a protostars. A protostar consists of the two regions, inner convective zones and the outer radiative photospheres. The boundary between the two regions is defined because the interior of a protostar becomes opaque. Opacity becomes larger. Then we could define the surface of a star. We cannot look at the very inner regions of a star. Actually, the inner region is a convective zone. We can use a polytope because this is adiabatic. So P is expressed K times rho to the 1 plus 1 over N. When we study the polytopic models, we derived these equations in the polytopic model of a stars. It is relation between mass and radius. So mass is a capital M. Capital R is a radius of a stars. And also same K appears here. So we can remove this K from these two equations. You can express the P to the N to the K to the N rho to the N plus 1. And also from the relation between the mass and the radius, K to the N expressed 4 pi G 1 plus N to the N Gm M to the N N minus 1 R over R to the N 3 minus N. You can substitute into the here and it becomes 4 pi R to the N N minus 3 D to the N over 1 plus N N N sub N N minus 1 M to the N minus 1 R to the 3 minus N. The rho density N plus 1. Then take a log in the both sides of the equations. So it becomes N log P equal N minus 1 log M plus 3 minus N log R plus N plus 1 log rho plus log constant values 4 pi R sub N N minus 3 G to the N over 1 plus N to the N M sub N N minus 1. So this is exactly equal to these equations, but you have to take a value at the boundary between the convective zone and the radiative photospheres. So you have a relation between the pressures, mass, radius, and the density at the boundaries between the two zones. Also, we could use other equations. So first one is a hydrostatic equilibrium. So pressure gradient is equal to the gravities. We consider the convective zone is massive than the radiative photospheres. So mass of the convective zones determine the total mass of a star. This M is a total mass, is a constant values. And the radius of a convective zone is much larger than the thickness of the radiative photospheres. So M and R is a constant values. So we take a radius and the mass of a convective zones. Then you could perform these integrals. In the both sides of the equations, integrate from the R to the infinities. The opacities, kappa is given by the kappa sub 0 times density to the A and temperature to the B. So we take a value of the density and temperatures at the boundary between the convective and radiative zones. So this is approximately K sub 0. Rho is the density at the boundary, rho sub R to the A. And the T surface temperatures, T effective temperatures to the B. So constant opacities we use. Then from the opacities, you can find these equations. Then from these two equations, we have a common factors of the density integrals. So we can remove this density integrals from the equations, take a log to find these equations. And also we could use the equation of state P equal K over mu M sub H times rho density at the boundary times the effective temperatures. Then take a log in the both sides of the equation, you will get these equations. And the luminosity is given by this equation. So take a log in the both sides of equations, you will get these equations. We have 4 equations, these 4 equations. Final equation we'd like to find is log L. Is a function of the log t and the function of log m. From the first 2 equations, you can remove the p. Then from the first equation, you have an equation for the mass, radius, density, and the temperatures. And also, we use the next 2 equations to find out this is also relation mass, radius, density we can obtain. Then from these 2 equations, you can remove the rho. Then it becomes mass, radius, and t effective. You will get a relation between the mass, radius, and the effective temperatures. Then you can express the R as a function of the mass and the effective temperatures. Then substitute into the equation for the luminosities. Then you will get a really complicated equation for the log L as a function of the effective temperatures and the mass of stars. Capital A and capital B given by these equations. So if you substitute the typical value for the low temperatures, n equal 1.5 and a equal 1 and b equal 4, then you can easily calculate to find that the capital A is 20 and the b is a negative 4. Then now we are ready to plot this on the HR diagrams. But the important point is A is a really big numbers. So you can easily imagine this is nearly vertical curves you would expect on the HR diagrams. So we call such a nearly vertical curve is a Hayashi Track because this path was discovered by the Hayashis. If you consider the regions with lower temperatures, we call the Hayashi's forbidden regions because this region is unstable regions dynamically. As I explained, once massive core is formed, materials start falling toward the cores due to the gravities. Then formation time scale of a protostar is about 100,000 years. Then stars start collapsing as a form of the protostar to form a real stars. So the star is following this track on the Hayashi track at first and then move to the transit to the Henier tracks. And then move to the main sequence stars. Start burning the hydrogen at the centers. This is the main sequence stars. Okay, so I explained how to form protostars from molecular clouds and then protostars HR diagrams. This is the end of the lectures for the formation of protostars.